In this video, I'm going to be doing a simple harmonic motion overview for AP Physics 1, which will be good review for any high school physics class or any introductory college course as well. We're going to talk about what is simple harmonic motion, what are some main traits and ideas to know about it, and how do you solve for the period of a pendulum or a spring. The second thing we're going to take a look at is we're going to focus on a pendulum, and we're going to do a full energy analysis, take a look at the TME, the total mechanical energy, and then analyze where there are maximum and minimum values for restorative force, for velocity, energy, and all types of values associated with simple harmonic motion. And finally, we're going to be taking a look at a spring oscillating back and forth, and we will be looking at some more graphs with our position versus time, velocity versus time, and acceleration versus time, and you'll kind of be able to compare and contrast the spring versus the pendulum with these two different scenarios. So let's go ahead and take a look at simple harmonic motion and check out some of these main traits. So with simple harmonic motion, we're going to be taking a look at a pendulum and a mass attached to a spring. And with both of these, they have a restoring force or a restorative force, which is a force that pulls it back to its equilibrium position, pushes or pulls it back. So say, for example, for the pendulum, if you push it out this way or it just naturally swings out this way, a component of gravity is going to have a originally came from, and then same thing from the other side. Same idea with the spring. If you stretch it out this way and it has a certain positive displacement, then it's going to have a force in the negative direction, and that is its restorative force. And a rule about the restorative force is that it is proportional to the displacement. So the more you pull this pendulum outwards away from the equilibrium position, or the more that you pull or compress this spring in, the more restorative force you have pushing it back to its equilibrium position. That is a main trait of anything that shows a simple harmonic motion. Secondly, all of these things have a capital T, which is a period, the amount of time it takes the object to move back and forth. And with these periods, they are independent of the amplitude. So what I mean by that is if this object over here that's on the pendulum, if it swings back and forth in a really wide, full arcing motion, or if it swings back and forth in a short little arc, no matter how much you pull that pendulum back and let it go, its period of how much time it takes to swing back and forth is actually going to remain constant. And the reason why that would remain constant, and just to put it simply, if you take a look at this orange arc over here, the arc length of that path right there is a fairly small distance. So when you have a smaller distance, you will also have a smaller average velocity, because if you pull it back, the component of gravity that's going to accelerate it isn't going to be quite as big as that green arc. And then for your green arc, when you pull it back, it has a greater distance to travel through, but it has a greater average velocity. Okay. In the end, the period is going to be exactly the same. Same thing for the spring. If you pull it a short distance away and then let it oscillate back and forth, it's going to move a little bit more slowly on average, but it's not going to be moving very much distance. And if you pull it out really, really far, it is going to release and then oscillate back and forth much faster across a greater distance. And in the end, the period stays constant. Third of all, we have a bunch of sine and cosine curves that are naturally produced when you take a look at the motion of these objects, whether you're taking a look at the energy, the position, the velocity, and so on. You're going to have all kinds of sine and cosine curves. Now, when taking a look at the period for both of these, the pendulum has its own formula. We'll call it T sub P, and that is 2 pi the square root of L over G is the length of the string, and technically that is the length from the center of mass all the way up to the very top of the string. That would be your L in meters. And your G value, you can go ahead and assume that is 9.8. unless you're on another mass other than Earth, which maybe you're on Jupiter or the moon. In that case, you might have a different G value. Other than that, you can assume that it's going to be 9.8 in most cases. And then for the spring, it has a different formula because it doesn't have the same properties as a pendulum. With this, we'll call it T sub S. And that formula is 2 pi the square root of m over k. M is the mass of the oscillating object connected to the spring, and then K is a spring constant measured in newtons per meter, which is basically how stiff or stretchy the spring is, how much force is required to stretch or compress it 1 meter. So using either one of those formulas, you can go ahead and find the period, the amount of time it takes to complete one full cycle for each of those oscillating systems. So now let's go ahead and focus on the pendulum and take a look at an energy versus time graph after we talk about some important values. So let's say, for example, we pull the pendulum back to position A. This is its maximum displacement from its equilibrium position, its equilibrium position being B over here. So we'll call this EQ for equilibrium position. And then this is when it's pulled back in the negative x direction, and this is the positive x direction. So A and X, or excuse me, A and C are where it's at its maximum displacement, or where it's showing the amplitude of the pendulum. Now at these points, the velocity is going to equal 0 meters per second. So when something swings as far as it possibly can, it's going to hit an instantaneous velocity of 0. Secondly, this is where you have the maximum amount of restorative force. We'll just call this force, and then I'll put RES as a subscript, and the maximum amount of acceleration as well, because force is directly proportional to acceleration. As I said before, there's a component of gravity that is going to pull the pendulum backwards towards its equilibrium position. So let's take a look at what that looks like real quick. So we have FG over here, which is parallel to the string. So that's not going to cause it to have any motion swinging back and forth. It's only a component that is perpendicular to the string. Now, when it's up here, we have FG pulling it straight down as usual from the Earth, but then we have two different components. We have a Y component and an X component. And this X component over there, which would be FG sine of theta, would be the perpendicular force that pulls it back to its equilibrium position. Okay, so same thing on the other side, except that perpendicular force is going to be pulling back in this direction. At the middle position, we do not have any restorative force, but we do have a special value here. This is where we have our maximum velocity. The reason why we have our maximum velocity is this. The way I like to look at it is if you're taking a look at this full arc from A to C, gravity as some component that is pulling it downwards over here, and it's letting it speed up for the whole first half of the swing, and the second half of the swing where it's moving away from the Earth, it's going to be slowed down. So it's speeding up the entire time from A to B. Therefore, B is going to be its maximum velocity, and then it's going to slow down from B to C and then hit a velocity of 0 at the other end, because that's where it reaches its maximum displacement or amplitude. And again, that's where you have the maximum amount of restorative force and acceleration as well. All right, so let's go ahead and get into the energy versus time graph, and let's take a look at what the kinetic energy looks like first. So the reason it looks like that is if we start from position A and release it from position A, it has no velocity at first. So if we are taking a look at the kinetic energy, which is 1/2 mv squared. If the velocity is always squared, the energy is always going to be positive, so we're definitely not going to dip below the x-axis. So first of all, it's going to start at a velocity of 0 because of the 0 meters per second, its resting position as it's released. And as it's released, it has the most amount of force in the beginning, so it's going to have the most amount of acceleration at the beginning, so that velocity is going to rise quickly and then less and less until it reaches its maximum velocity at this equilibrium position right over here. And then this is going to be position A, where it is the negative x position. And then as it rises up towards C, it's going to feel more and more of that restorative force, which is going to cause it to slow down and reach 0 once again. This is position C, where it's at its positive X position. And then that restorative force is going to slow it down, make it go to 0, and then it's going to send it back the other direction. And then remember, it's not going to dip below 0 because it's v squared. So it's going to cause it to speed up and reach its maximum kinetic energy and its maximum velocity back to its equilibrium position again. And then as it rises up or continues to rise up towards position A, it's going to slow down, and it's going to slow down at an increasing rate. So if it's slowing down more and more, it's going to go towards 0 faster and faster, and then it's going to hit position A once again at its negative X position. Now that would be considered one full period because we started at A, which is the negative X position, all the way back to A, its negative X position once again. Now for the gravitational potential energy, which is GH, that's largely just going to be determined by the H value, which is the height. This would probably be our baseline height. Let's go ahead and make this a different color. This is probably going to be our baseline height right over here. At the very bottom of our swing, we'll call that 0 meters. And this one is actually going to end up mirroring this graph over here. And at the beginning, where it starts at position A, is where it has its maximum height. And then its height is going to drop quickly because it has that large restorative force in the beginning. So it's going to start from position A, the negative X position, and then move towards a height of 0, where it reaches its equilibrium position. And then the rate at which it's increasing its height is starting to increase in the beginning, and then the rate that it gains height is going to decrease towards the end because that restorative force is pushing back on it, and then it's going to reach point C, its positive X position. And then that restorative force is going to make it lose its height fairly quickly in the beginning and a little bit less at the end when it reaches back to its equilibrium position. And then it's going to finally swing back up to its final position, position A, its negative X position. And it should always basically like mirror or be symmetrical to this invisible horizontal line right here, because kinetic energy and gravitational potential energy transfer to one another and have an inverse relationship. And then if you want to take a look at their total mechanical energy would be a line that looks something like this. And that orange line would be your TME, your total mechanical energy, which is the sum of these two. And that is going to stay constant because the energy is conserved in a closed system. The energy is just being converted back and forth from kinetic to gravitational and vice versa. Now going to our final scenario, we're going to take a look at a block oscillating back and forth as it's connected to a spring. And that force, that restorative force that it feels, can be represented by Hooke's law, F equals negative kx. And that negative is because it is a restorative force. So let's say, for example, our scenario is that it's moving through its equilibrium position right there, and then it's going to move to the maximum amplitude that we'll call positive x, and then it's going to reach a velocity of 0 at its maximum displacement. That's where it's going to reach its maximum restorative force and acceleration as well. And then same goes for its greatest negative displacement as well. It has a velocity of 0 and it has a maximum restorative force just pointing towards the other direction, towards the right, because it's compressing the spring. So the spring is going to push to the right. So that's where it's going to have the maximum restorative force and acceleration as well, just in the other direction. All right, so let's go ahead and take a look at these graphs. So if you're thinking about what's happening with the position versus time graph, I think about it in terms of slowing down and speeding up, and also in which direction. So we're going to call this direction positive and then this direction negative. So from the equilibrium position to its maximum positive displacement, it's going in the positive direction, but it's slowing down. So we're going to rise on the graph and we're going to make our slope progressively more flat. And then that is going to be our positive x value from its equilibrium position. And then as it gets pulled backwards, remember it has its maximum amount of force over here. So it is going to move back steeply towards the other direction. And then as it does that, it's going to hit position 0 right over here as it moves through the equilibrium position. So it's going to move in the positive direction and slow down, and then it's going to speed up in the negative direction and then hit 0. This is where it's at its equilibrium position one more time. And then now it's starting to compress the spring. So it's going to slow it down in the negative direction. So we're going to go underneath 0, but we're going to make sure that slope becomes more and more flat. And then as that restorative force over here pushes back in this direction, because the spring is compressed, it's going to give it the maximum amount of restorative force, and it's going to cause it to speed up towards that equilibrium position. So from that negative x position, it's going to push it back to its equilibrium position. And then we're going to get a nice little sine curve there. And then when you go to your next graph, you can do that a couple ways. We know that the slope of our position time graph is basically delta x over t, which is the velocity. So you can produce your velocity graph one of two ways. You can basically think through what's happening to the velocity through the equilibrium point at our positive x position, our negative x position, etc. Or you can take a look at the slopes of your position versus time graph. Okay, so whichever one is your strength, I would definitely go there. So for the position versus time graph, we have slopes that are going in the positive direction, but it's positive and becoming increasingly more flat, and then it's hitting a instantaneous velocity of 0. So it's going to look something like this in the beginning, and here's our instantaneous velocity of 0 at this positive x position when it's coming from the equilibrium position. All right, so here's where it's at its maximum stretch. And then from here to here, now it's dropping down in the negative direction, and it is becoming greater and greater in the negative direction until it reaches its maximum velocity, maximum negative velocity at the equilibrium position right over here. Okay, as it sweeps through its equilibrium position, it is going to move closer to 0, which means that it is slowing down because now it's going through its equilibrium position and starting to compress the spring. So the spring is fighting against it to make that velocity that is a large negative velocity move towards 0, which means it is slowing down. And then at its greatest restorative force, it's going to push it up with a fairly steep slope, and then that's going to start to flatten out a little bit towards the end. So this is where it has its greatest negative displacement before the spring pushes it back towards its equilibrium position. And then finally, we're going to take a look at the acceleration graph. And that you can also do one of two ways. You can take a look at the slopes of your velocity graph. So we know the change in v per time is the acceleration, or again, you can kind of think of all the conceptual ideas of the restorative force and acceleration as the spring is oscillating back and forth. So the way I look at it is thinking about what's happening with the force. Remember, the force and the acceleration are directly related to one another. So whatever the force is doing, the acceleration is also doing as well. So the first thing the acceleration is going to do is it's going to start at its equilibrium position and temporarily not have any acceleration at its equilibrium position because the spring is neither stretched or compressed at that point. And then as soon as it passes the 0 point going towards the positive direction, it's starting to stretch the spring, and the spring is going to pull it back towards its negative direction. So it's going to have more and more negative force until that force is going to max out at the positive x position. So remember, once the spring is pulled all the way to its farthest point, that's where it's going to have its maximum restorative force. That's this maximum negative acceleration because it has a maximum negative force. And then it's going to pull it back to 0. So it's going to have less and less negative force until it reaches that equilibrium position. And then now it's starting to compress the spring. So the spring is going to fight back against it and push to the right. So now we're going to go into the positive region. And then we're going to have more and more positive force until it reaches its maximum positive force at its greatest negative displacement because it's compressed as much as possible, so it's pushing back a lot. And then as it pushes it back to its equilibrium position, it's not going to be pushing quite as much until it pushes not at all at its equilibrium position to end off. Okay, so again, I like to think about it in terms of force because force is directly proportional to acceleration. So for me, conceptually, that kind of makes a little bit more sense. And now we have completed our acceleration versus time graph and completed one full period for the position versus time graph, velocity versus time graph, and acceleration versus time graph. So to sum things up, when you're analyzing things in simple harmonic motion, you're basically taking a look at different energies, positions, velocities, and accelerations, producing all kinds of different sine and cosine curves based on how the values change. You just have to be aware of how the restorative force and acceleration are working and where there are minimum and maximum values. So I hope that was helpful in helping you understand all of those ideas. Thank you very much for watching and listening.